Okay, I think this last video will probably be quite short. Really, I'm just going to be talking about filters as applied to audio, to digital audio. We're going to be looking at low-pass filters, high-pass filters, and band-pass filters. Mostly these are fairly self-explanatory, but I will quickly go through them and give you examples. Essentially, filters let you manipulate sound. You're all familiar probably with a tone control that you would use on your radio or on whatever audio device you use, where you can adjust whether you want more bass or more treble or whatever. Filters are kind of a fancy version of that. A low-pass filter is designed to let frequencies below a specified cutoff to pass through and reduce or eliminate the frequencies above that. High-pass filter is exactly the same in reverse. It lets high frequencies come through, and frequencies above a specified cutoff frequency pass through, and any frequencies below that it strives to reduce. I'll show you some examples. I should have showed you the low-pass one before. Let's get rid of this one. So this example is just using white noise as input. What I probably should do yeah, that's right. What I should do is this. Instead of using white noise, let us use our example that we've been using throughout this little series of go down gambling. Now I'm going down gambling. What's going on? Classic newbie error. Didn't turn on the digital audio, did I? Make sure the DSP is on. So, as you can hear, as I'm manipulating this low pass filter here, which is called LOP in Pure Data, it's filtering out a greater or lesser amount of the audio signal. So at the moment I'm sort of saying, well, cut off everything below 10 Hertz, which is basically all audio in a way should be inaudible now. You won't be able to hear it. I can just hear a very faintest hint of the song coming through the speakers. And as I bring this number up, we're now saying let through everything below 200 Hertz. Let me just move this around so you can actually see that number properly. So this is our cutoff frequency at the moment. So everything below 200 Hertz should be audible, and everything above that should be inaudible. I mean, in practice it won't be inaudible, but it will be reduced. As the cutoff frequency gets higher, we hear more and more of the original audio, until eventually we're hearing pretty much the full signal. Let's just cut that out for a sec. You can also use, obviously you can use any arbitrary signal. If you use white noise, filtered white noise gives you quite a useful synthesis sort of building block. As you can hear, as I move the filter values around, we're getting some nice sort of, windswept beach type sounds coming through there. So sort of the inverse of additive synthesis in a way is subtractive synthesis, where you actually start with white noise and add more and more and more filters of different values together until you filter out all the noise you don't want and are only left with the noise you do want. So it's kind of like, it's like additive synthesis, but kind of the inverse of that, called subtractive synthesis, that you could look up if you're interested in this kind of thing. But hopefully from that you get a sense of what a low pass filter is. And it should be fairly obvious, I would expect, what a high pass filter is going to be like. Let me, again, we'll use our use the sound from Go Damn Gambling with the audio on, volume up. So as you can see, as I'm scrolling this, as you can hear, as I'm increasing this frequency value, we're letting through less and less of the original signal. So now we're only all frequencies above about 2000 Hertz through now. We type in 10,000. We're starting to cut out almost everything which is audible, getting closer and closer. 15,000. So a high pass filter, same concept as a low pass filter, only we're working with high frequencies now. Only frequencies above the cutoff frequency will be let through. A band pass filter lets you specify the frequencies, a frequency range that you're interested in. So it will, you can specify a specified band which should be allowed, frequencies that should be allowed to pass through, and everything below or above that band of frequencies should be reduced or removed. So the graph of the filter looks something like this. Frequencies that are in this range will be let through. Frequencies outside the range should be attenuated, reduced down to 0 in theory. The sharpness of the filter, how small the range of frequencies is that you're allowing through, is known as its Q value. So let me open up an example of that. And again, let me use our Blood, Sweat and Tears example. So here we are specifying the center of our band pass, the center of the frequency bands that we want to pass through is 500 Hertz, and we've got a Q value of 1. If I move the frequency up, now we're tuning into the higher frequencies. If I make the Q value, if I increase the Q value, we get more and more selective. So now we're saying a much narrower range of frequencies around 9,000 Hertz. The higher the Q, the less you're letting through. So I've got quite a high Q value there of 18. And as I bring the center of the bandpass down lower through the spectrum, we're now sort of tuning into the more mid-range frequencies. Try and keep the volume as high as I can. And now we're getting down to the much lower bassy frequencies. Okay, that's it. So that's filters in a nutshell. In a practical sense, we're not going to go into mathematically how they work or anything like that. It's enough for you to know that they exist and that there are low pass, high pass and band pass filters, and for you to have a sense of what they sound like and when you apply them to a digital signal. So in the lab you'll be, I encourage you to have a play around with those and think about how you might incorporate them perhaps into your projects. Okay, I will see you in class.